But I want to thank you very much for allowing me to give a little bit brief introduction. And so the next thing that we're going to do is we're going to talk about a welcome to Ultra Ethernet. Now, unfortunately, here's the problem. The speaker who is going to be doing the welcome to Ultra Ethernet is sick. And so, hi, my name is Jay Metz. I am the chair of SNIA, and I am the chair of Ultra Ethernet, and I am going to be playing Craig Carlson today, who is going to be your originally scheduled speaker. So I hope you can differentiate me with the earlier speaker in some way. What I'm going to do is I'm going to give you a brief overview. We only have about a half an hour to talk about this. And so this week, SNIA has been co-located with Ultra Ethernet. We've been working together from the storage side and from the data side. But Ultra Ethernet itself is far more expansive and ambitious than we've got for just storage. So I'm going to give those of you who may not be as familiar with Ultra Ethernet a bit of a background as to what we're looking to do and why we're trying to do what we were doing. And if you're not used to being in Denver in the high altitude, please do drink a lot of water. Okay, so Ultra Ethernet. What is Ultra Ethernet? Why did we do it? Well, when we started doing a little bit of history lesson, when we started doing Ultra Ethernet back in 2022, there was a question about how we were going to handle the networking requirements for very large scale environments. AI, HPC, ML, all of these different topics were starting to put pressure on the network to be able to handle some of the needs that as you get to these large scales, right? So if you're used to normal networking, normal general purpose Ethernet networking, you're not used to really large systems, right? They're not incredibly large, but the kind of workloads that we've been talking about and where we're looking at doing it is huge, right? HPC, for example, not uncommon to be over 100,000 endpoints. You know, and at the time, the largest HPC possibility was around 250,000 endpoints. And it was growing so fast that people were starting to become a little alarmed that there wasn't really a way that we were going to be able to handle some of the model sizes that were being created because of the way that the networks work. So as we started to look at this, we said, we need something that's going to be incredibly performant. The big problem is that as you get bigger in your networks, right, with the number of endpoints, and with the traditional networking size, you wind up with effectively a networking tractor pull. Now, if you're not familiar with a tractor pull is when you have a tractor with a weight that sits on the back, and as the tractor moves forward, the weight moves forward, makes it almost impossible until the engine goes boom, right? So that's the kind of an issue that we have with a network in a large-scale environment. The more that you scale, the more inefficient your network becomes. That is a problem. So Ultra Ethernet was designed to handle this performance problem, this efficiency problem, and become the proper solution in an open manner for handling the AI and ML and HPC workloads. Now, the other problem that we had is that, well, you could do this on your own, right? You could create your own proprietary system, and that is entirely possible. But we figured out that Ethernet was probably a really good way to go, simply because of the fact that there's an entire cottage industry of Ethernet admins. Right? You don't have to build a whole new administrative cottage industry because of this. You have best practices already put in place. You have a good understanding and a full stack that you can build on. So do you want to build a whole new network, or do you want to stand on the shoulders of giants? So Ultra Ethernet was designed specifically to do just that. We wanted to make sure that you had a really good, cost-effective approach to solving problems that you were already familiar with, and you didn't have to swallow the whole pill all at once. You could add in things over time. Okay, so what is it? How do we do this? Well, this was actually one of those questions that was pretty interesting, because this is a big problem. It's a big problem to solve. Because what we were looking to do is take Ethernet, which is designed specifically to be a general purpose network, and make it a very specific purpose network. Right? The reason why Ethernet is designed the way it is, the layers that it is designed the way it is so that you can create a general purpose that covers all kinds of different workloads, all kinds of different scenarios. And what we were trying to do is tune that so that it actually could be really good for HPC, could be really good for AI, and that was a little bit more ambitious than people realized at first. So what we did, we started off with the four general relationships with what mapped to the OSI model. Your physical layer, your link layer, your transport layer, and then your software layer. It's a rough mapping, okay? And then what we did was we said, you know what? How do we know this is going to work up and down the stack? Obviously, we want to tune it. So we need to make sure that there's a vertical checks and balances and accountability from the physical layer all the way up into the software layer. And so we created these four different vertical pillars, right? We've got management, storage, compliance and debug, performance and debug, right? Compliance and test and performance and debug. So why do we do this? Because we want to make sure that when somebody is going to implement UEC, they can trust that it's going to work all the way up and down the stack and it's not going to interfere with each other. As you can imagine, that is a big problem to solve. So when we started accepting members in November of 2023, we thought that there were going to be a few people who were going to want to join. Well, within 6 months, we already had 50. And now we have over 120, a year and a half later. We are the fastest growing project inside of the Linux Foundation in history. It turns out this is a problem that a lot of people want to be able to work on and to solve. So ultimately, that is our main focus, right? Our focus is to create a full stack environment that builds on the shoulders of an existing environment that people well understand and make it more efficient specifically for the workloads all across the board. And we do this specifically by saying that each of these workloads have specific needs, and we'll get into this a little bit later, specific needs that allow us to be able to do certain tweaks that will become aligned like a pachinko chip down the stack and then back up the stack to make sure that you get the most efficient, best utilization, and highly performant network at large scale for these kinds of workloads, because it's all supposed to work in concert. So who's here? Well, the original steering committee members of 10 companies are still there, and so we've also added in a whole bunch more. This was as of October of 2024, and we've had several more since. We have we get about anywhere between 1 and 5 new company applications a week, right? We're still getting those applications, and so this is an out-of-date slide, but you can get the idea that this is one of those things that is a big problem that people all are trying to address and trying to solve. So what are we actually talking about when we talk about UEC networks? It turns out that this is not necessarily one of those things that's intuitive. Generally speaking, you start talking about a better network, you start talking about an efficient one, you start talking about the ability to reduce tail latency, you want to make it big scale. Well, can we use this anywhere? What we're looking to do, and this is where I'm going back to back to basics here. We're doing this specifically for a network that is purposely designed for a specific workload characteristic. So we have effectively three different network types that we're trying to work on. The first is the general purpose Ethernet that everybody knows and loves, right? It is also, from a storage perspective, the network that you usually find your data, right? What we're talking about in Ultra Ethernet, and as a starting point, is the back-end network, the network between accelerators for a scale-out approach. Because what happens is when you look at the workloads, you have specific roles that are played in each of these different devices, and those roles have to communicate, and those devices have to communicate with those roles. And there's different types of applications that are different types of workload requirements. Collectives, for example, like all reduce, they have specific types of data transfer requirements, and that's what this network does. Another back-end network that is specific is the inter-device communication, right, of basically scale up, which means that I'm going to take the memory locations of a GPU or a TPU, and I'm going to combine it with a whole bunch of other memory locations of other GPUs and make one big, huge honking one. So that's the difference between the different network types that we're talking about. UEC is focused in 1.0 on getting those big, huge honking GPUs to talk to each other and get those roles to be played in the proper sense and make sure that the data traffic is actually working in the most efficient manner. So it's that middle area that UEC is focusing on for 1.0. So why don't we just use normal Ethernet and normal Rocky? Well, like I said, this is the tractor pull problem. The tractor pull problem is that with something like Rocky, the more links you get, the less efficient it gets because you wind up having to lock off certain types of paths. What we want to do is we want to say, if you've got these kinds of environments where you've got, the networks going out across a major fabric, you want to be able to use all the links. And you want to be able to use all the links in a fine-tuned, granular fashion. And that means a couple things. One is you want to be able to handle out-of-order packet delivery. Right? That is an incredibly important thing. And some of the applications do very well with out-of-order, some of them don't, which means you have to create the reliability that goes along with that out-of-order message delivery. And then we also have to make sure that it's secure, right? So built into the actual into the transaction is the optional security keys. Now, not every deployment, not every application needs to have built-in security, and the really low latency stuff may not necessarily want it, so it's an optional feature, but it is built in from the ground up so that it doesn't have to be added on later. We want to do we want to do packet spraying, which is packet level multipathing. So what winds up happening is that you effectively, when you've got a flow level packet, you take the flow and you take the exact same path for the entire flow. With packet spraying, you can send packets over every different link that's available, and you are able to effectively have communication back and forth between the endpoints as to which paths are the most reliable, which paths may be congested, and which paths you want to use for any kind of retransmission. And there's additional information inside of the packet header that says exactly where it needs to go, all the way into the memory regions on the endpoint. So all of this information is embedded inside of the packets. Now what that allows you to do is create these transaction-based approaches so that each transaction, each flow that goes over is effectively its own entity. You don't have to maintain state across a really large network. Oh, please put that on pleasure mode. I appreciate that. Thank you. Okay. All right, so, and then we've got to that point, we need to make sure that you have the ability to communicate about congestion across the network. So we have two different types of congestion that are appropriate in certain types. We have a mandatory sender-based congestion control, and we have a receiver-based congestion control. And they're both useful for certain things. The receiver-based is optional and allows you to do some additional tweaks and tricks inside of these environments to help avoid some of the incast problems that can come up in large scale. The sender-based approach allows us to effectively use the round trip time and some additional magic under the scenes that will give really flexible, very quick responses to congestion from a sender that doesn't require slow ramp-ups. So obviously this is a really high level. I can't go into the detail. Once we start to get past the 1.0, which should be coming out very shortly, we'll go into much more detail about what it is that these congestion control mechanisms do and how they work. So this last point here that I wanted to bring is at the semantic level aspect. What we do is we create a different semantic for the different profile types that we've got. So we've got an AI profile and we've got an HPC profile. And those profiles have certain semantics. And what the semantics mean is that when we have the API that comes in from the top, which is a libfabric API, it talks to a specific semantic profile. That semantic profile identifies what the requirements are based upon whether it's HPC or AI, and then it talks to the packet delivery sublayer, and that packet delivery sublayer then identifies whether it's reliable unordered delivery, reliable order delivery, and then it continues to work down the chain, and that's how we actually connect the dots. Okay? So that semantic architecture is a very fundamental and required key point of what makes UEC UEC. The semantic profiles are, and the corresponding tie-in to the packet delivery sublayer is what makes UEC do its magic. And then the last part of it is, well, what can you do with this? Well, the idea is that you're going to want to create an environment that go up to a million endpoints. 1 million endpoints. Well, why do you want to do that? Well, up until very recently, an endpoint was effectively a port on a NIC, right? That's not the case anymore. You can have an endpoint be anything. You can have an endpoint be a NIC. It can have an endpoint be a port on an accelerator. It can be a port on a DPU. It could be a lot of different things, right? Or it could be a virtualized port on any one of those different things. So an endpoint in and of itself is actually starting to explode. You start with these clusters, with these really large training models, and all of a sudden you start to realize that the networking requirements are just exploding. So what constitutes an endpoint is, I won't call it a happy accident, it was by design, but we realized that when we started doing this, that it wasn't going to simply be a matter of 10, 100, 500,000 nodes, right, or 500,000 endpoints. What constituted an endpoint was going to evolve, it was going to morph, and we needed a design, and we needed an architecture that was going to go along with it. Okay. So what does this mean? Well, AI workloads and HPC workloads are similar, but they're not exactly overlapping. Okay? So for instance, one of the things that happens in AI is you find yourself with a lot more small packet, bursty size traffic, and with HPC you often get really long bandwidth heavy throughput requirements for those types of things. But what happens when you scale? What happens when you scale is that these Venn diagrams start to overlap a bit. Okay? So for example, let's just take a training model for instance. A training model has a lot of different steps. So a workload like AI is not actually one workload. It's multiple workloads. And as you get bigger with a larger scale, with the larger parameter sizes, you start to realize that the amount of metadata that goes back and forth is starting to overwhelm the actual data that gets trained. Right? So when you have these multiple devices, I've got an accelerator here, I've got an accelerator here, and they're working in parallel, they have to be able to agree. So if they don't agree, then you have a big problem and you have to roll back to a previous state. So I need to make sure that the communication that goes between these two different points is going to be in sync. That's a lot of network traffic that goes back and forth that is not related to the data that's being trained. So that's a metadata problem. And it is a networking problem because it is not the same type of network traffic that exists inside of a training data movement. Okay. So what happens when you're starting to do these kinds of things with an HPC? Now we're starting to see these types of small data types be more prevalent at larger scales. Okay? So we have to create transport primitives that accommodate these things. Accommodate the large scale with the multipathing because that data may not necessarily be going in a prescriptive manner or a deterministic manner. So we want to be able to use all the links to get that type of data, whether it be the metadata or the training data or the checkpointing data to be able to be handled properly. Then we have to modernize the congestion control because once you start to get to these really large systems, the hotspots come up unpredictably. Are you familiar with the concept of complex adaptive systems? Okay. No. Just you, Jay. All right, fine. Basically, the idea in a complex adaptive system is that you have what's called the situation of autopoiesis. Maybe you may be familiar with Conway's Game of Life, right, from the 1960s. Basically, Conway's Game of Life effectively had the ability to, it was in a simulation, which essentially grew cells based upon some very simple rules. And the test was to see whether or not these cells grew into a colony or died off. And it would just happen based upon these very simple rules. And you'd find hotspots of the colony growing and then also dying, and it was all based upon the rules about whether or not there was something adjacent to it. But the premise is that you don't have a command and control architecture about when these things happen. Based upon some very simple rules, you can find up with some hotspots. Hotspots of a community, in that case, hotspots of congestion that are unpredictable inside of a large-scale environment like HPC or AI at 1 million endpoints. So we have to be able to have a very proactive and aggressive ability to solve congestion issues before they get to be too much of a hassle. And that's one of the things that we did. At the same time, we want to be able to work with applications that do use RDMA. So we're working on handling the RDMA optimizations as well. So all these things are supposed to bring us to a specific end goal, which is to improve the performance, improve the efficiency, and improve the tail latency because the workloads have different types of characteristics. Like sometimes all of a workload needs to go to one. Right? One GPU needs to collect all the information, and sometimes you need to send all that data to all of the different GPUs. Those require a very flexible kind of networking environment. Okay? So those are our key goals. High utilization, can't talk today. High utilization and very low tail latency is our goal. All right? So this is a partial list of the work that has been going on. As I said, we've got 8 different workloads, and the first ones were the 4 horizontal ones. So we'll go through a little bit of these in a little bit more detail, but not much. We don't have a lot of time. But at the very top of the layer, the applications that are being run for AI and HPC usually use, or they often use, the libfabrics API. So we've adopted the libfabric API to be able to handle the connection between the upper level application protocol without us having to rewrite our own, and the underlying semantic layers and transport layers. That is a very robust and significant aspect of how UEC works. So then underneath that, we have the ability in the transport layer to handle the multipathing, handle the ordering of the delivery, whether it's reliable or unreliable, and we have the ability that's when it goes into the management for the congestion control. All that's being done inside of the transport layer. We're working on finishing up the in-network collectives at the transport layer as well, which will be slightly later than the 1.0 release. But it is an important part, as we've been talking about, making sure that we have additional functionality inside of the network to be able to handle those kinds of traffic patterns. At the network layer, we don't do a lot of the stuff at the network layer. We use bog standard IPv4, IPv6, ECN, and there's an optional trimming factor that allows us to do a quick notification to the sender if there's congestion at the end receiver for the receiver-based congestion control. At the data link layer, we have your typical, if you're used to LLDP, that's what we've adopted for the discovery and the configuration at the links. And then we've got an optional link level retry that if you've got a failure on the link, you can actually do a retry that is supposed to be helping at the smaller layer for any errors that happen. Underneath that, the physical layer is going to be starting off at 100 gigs so that you can have the backwards compatibility of existing 100 gig switches that exist in the network. It's an endpoint-oriented protocol. And so you can be able to put this into an environment without having to do a forklift upgrade. You can use existing 100 gig switches, and there's an optional function about being able to use control order sets that is able to get a signaling back and forth between the link layer and the physical layer that helps improve the efficiency of any kind of error recovery that goes along. Okay, so quick up and down the stack. At the top, we've got the modern remote memory access for HPC and AI. It's a bit richer than the socket approach to solving this. And this is a bit of a slightly deeper iteration of what I had just said, because this is basically the way that the sequence and the hierarchical decision making is done. So at the transport layer, the API comes through. Sorry, the characteristics come through the API into the transport layer, where it is then identified by the semantic layer as to what the requirement for UEC needs to be. It's communicated into the packet delivery sublayer, which says, okay, this is an AI profile, therefore it's going to be this. If it's an HPC profile, it's going to be the reliable, with idempotent operations. And then it goes off to the security. Do we want to use security or not? And then we identify which congestion management system we're going to use for which profile, and that we basically, like I said, goes down through the layers to make sure that they're all aligned. At the network layer, come here. Oh, did I go in? Oh, and then we basically have the multipathing and the routing ability at the transport layer to be able to use all the different links, and it allows us to use out of order delivery, and still yet be reliable, especially for those sensitive types of traffic. At the network layer, we still use the DSCP and QoS that is standard for IP, and we also have the packet trimming opportunity, which allows us to, in a congested environment, trim off the payload and send a header back off to the sender, where they can then do the retransmission of a packet, because the sequence is still embedded in there. So they know that there's been congestion, the payload has been dropped, and needs to be resent. That's an optional feature that is used with the receiver-based congestion control. And then at the link layer, we're using effectively standard Ethernet with an optional link level retry for error recovery. So what about storage? This is after all the SNIA developer conference, right? So we formed one of those vertical pillars inside of UEC is the storage work group. And the idea is to create an environment with storage that is indigenous on the UEC network. Remember I said that the storage environment is on the front end network. What that means is that when you start to do a packet walk of how the data gets into a UEC network and gets out of a UEC network, there's a lot of tromboning that goes back and forth between the networks. There's no data indigenous on a UEC network. You have to go outside and bring it back in. You have to checkpoint it outside and bring it back in. That's not an efficient way of doing things, and it winds up creating a lot of additional latency in the epoch. So one of the things that we're doing inside of UEC and working, we've got a relationship with SNIA to work on specific projects in the future, is to create a storage environment that allows us to do object, file, and block. Our first go is the NVMe over Ultra Ethernet. UEC has a relationship with NVMe to do this and work on this in an official manner. Excuse me. And it is an environment that is going to effectively wind up helping certain phases of a AI workload. Hopefully, one of the things that people are actually looking for in the beginning is how can we make the checkpointing more efficient? Checkpointing is one of those things that people kind of, again, like when you lose your data, you suddenly realize it. Checkpointing is one of those things that people kind of say, yes, you have to do it, but they don't focus on it when it's required. But checkpointing is actually a science and an art unto itself. So what we're looking to do is use this as probably a checkpointing starting point, but there are other aspects of data that need to be done indigenous inside of the UEC network. And that's one of the reasons why we're starting here. So first of all, NVMe over Ultra Ethernet allows us to give a major boost for block-based protocols. And we've got a number of things that are going on inside of the NVMe working groups that allow us to do some very cool things if we start to move the processors closer to the data themselves, right? So data doesn't necessarily have to mean, it means persistence, but data also could be, computation near memory, computation near storage, and one of the things that you'll probably hear a little bit later on is how that can work in an HPC environment, for instance. So what we want to do is we want to create the ability for UEC to talk natively into the NVMe over fabrics. Right now it doesn't talk natively, it talks natively using the front-end network, and so that's the work that we're doing inside of UEC to do this. So one of the things that we don't typically have in HPC environments is NVMe. We usually use parallel file systems or object. And one of the things that we're trying to explore is whether or not this is something that we could use in an HPC environment as well. So because Ultra Ethernet does have HPC profiles, then having a storage profile that make the storage co-located on that network is a future goal as well. So to that end, the first project that we're working on is the NVMe over Ultra Ethernet. We have created an MOU, and it has been signed, sealed, and delivered between UEC and the NVMe Express board. That is now official and underway. And it's going to look very similar in its structure and its nature to NVMe over RDMA. And so one of the things that we're probably going to have to examine is, just how do the semantics look when it's all said and done. And one of the interesting conversations that happened this week, as a matter of fact, was what does that semantic look like from an RDMA perspective and a UEC perspective with NVMe Express. So we're working with NVMe Express on that and making sure that we have that collaboration across the industry and not trying to reinvent a wheel that doesn't need to be reinvented. So in summary, I want to point out that the Ultra Ethernet, perfect timing, I'm almost out of my voice. That Ultra Ethernet is an incredibly ambitious project. In a very short period of time, we have managed to create an incredibly robust and thorough document for multiple different work groups spanning, I think it's going to be something along the lines of, 600 to 800 pages, and we did it all in less than 2 years. All right? And so the amount of dedication and work that's gone on inside of Ultra Ethernet is amazing. And that's not including the work that is currently going on for the additional 4 groups on compliance, storage, management, and performance. So we expect that Ultra Ethernet is going to be around for a long time in an open ecosystem environment and be able to encourage people to use with high trust this particular protocol for these types of workloads. But we're just beginning. We got a lot of work to do. We have a lot of things that we have to do in the future. And so this is one of those things that is not a flash in the pan. We've got a long path ahead of us to be able to work. So I want to thank you for the time. Thank you for allowing me to lose my voice in your behalf. And you can always ask me the questions a little bit later on. We have a question?
Any questions?
Oh, great. It's Andy.
Hey, a couple questions. Is this on?
Yep.
Okay. Are you actually addressing security over RDMA?
Are we progressing security over RDMA?
Yes.
No. No, okay. we're handling security only as it becomes part of the packet delivery sublayer.
Okay. Do you have any handling for connection redirects with NVMe over Ultra Ethernet?
You're going to have to repeat the question.
Do you have any provision for connection redirects with with NVMe over Ultra Ethernet? That was one of the failures of NVMe over TCP, is they got rid of connection redirects that OSCSI counts on.
I do know, so one of the things you're asking is what is the impact on multipathing on and packet spraying on NVMe Express, right? On NVMe traffic.
Yes.
Right. And so that was a hot topic of conversation this week. And as far as I know, it is a discussion that's going on. It is a concern. But we're still in the early stages of that. But yes, it is being discussed.
Okay, and final question is, for the checkpointing issue, are you addressing this by possibly doing connection mirroring or connection multiplexing so you can both checkpoint and do data access at the same time?
Okay, so you're asking a lot of the mechanics of how this is supposed to work, which is still in the early stages
Okay.
and haven't been decided yet.
Okay, good enough.
Yeah.
It's-
Yeah, but these are all extremely valid and important questions that have been done. Like because the thing is that we have a different model in storage traffic than what Ultra Ethernet is typically being used for, and so all of these different aspects of reliability and ordering is a prime consideration. Now, whether it wind up being mirroring in the future is a player to be named later. Any other questions?